Hello everybody. In this video we'll dive into the cutting stock problem, which is a very common problem in logistics, and we will tackle the cutting stock problem initially with basically beam packing formulation, and then we'll use column generation to solve it. So in terms of content, as already anticipated, I will first describe the problem setting. I will describe a beam packing formulation. I will just give you the formulation without solving it explicitly. And then in the second part, we'll have column generation, so a path-based formulation as expected. And I will also be showing you a Python implementation. So without further ado, let's start with the first part of the video. So what's the cutting stock problem? It's a very important problem in many logistics application. In the original variant, as you know, there might be many variants like the vehicle routing problem or other classic operations research problem, but in the original variant of the cutting stock problem, we have to cut standard sized pieces of stock material such as paper rolls or sheet metal into pieces of specified sizes. And the idea is to minimize the material we waste in the process. For example, let's assume we have a paper roll which is 20 meters long. If we need to cut pieces of 5 meters, that's good because for each roll we are not wasting anything pretty much. At the same time, if we need to cut pieces of 8 meters, we can actually cut 2 pieces out of this paper roll with a waste basically of 4 meters. So the idea is we have a set of rolls, could be 2, could be 5, it could be 10. Usually it's implied there's enough capacity that we can actually cut all the pieces we need. So usually in practice there will be, but in this context there's no upper bound of the number of rolls we use. And we have this demand. So we have different customers might require us to cut pieces of different length. So the idea is how to properly mix these pieces into our rolls in order to use basically the smallest number of rolls possible. And with the beam packing formulation, we do like this. We have 2 sets. The first set is I, the set of items, and the second set is B, the set of beans we have available. We have 2 parameters. Well, one is actually a set of parameters, Li, which is the length of item I, and the other one is L, which is the length of each bean. One thing I didn't specify is we have a homogeneous set of beans, so they're all equal in size, and well, that's actually the only characteristic we care about. And we have 2 decision variables. We have xib, binary, which is 1 if item I is allocated to bin K, actually it should be B, sorry, I will fix that, and 0 otherwise. While yb is also unitary, is also binary, and it is unitary if bin B is used and 0 otherwise. So, what's our formulation? We want to minimize the summation of our YBs, and remember, YB is 1 if we use bin B. So basically we want to minimize the set of used rolls. Let's stick with the paper rolls example. Constraint 1 says that each item should be allocated exactly to 1 roll. Constraint 2 basically says that whichever subset of items we allocate to a paper roll, the summation of the lengths of those items cannot exceed the length of the roll. Basically, we need to cut feasible pieces overall from a single roll. The third constraint is somehow related to the second one. It says that an item can be assigned to a roll if and only if that roll is being used in the first place. And then constraints 4 and 5 define the nature of our decision variables. And this is just a recap of what the problem entails. We want to minimize the number of used beans, and we do so by requiring that each item must be assigned to exactly 1 bean, and the length of all items associated to a bean should not exceed the length of the bean. Again, I'm using bin and role interchangeably. Bin is more general, role is more specific for the example. And the third constraint is we can assign an item to a bin if and only if that bin is used in the first place. So now let's dive into column generation. So we want to solve the same problem, we are not changing the problem, but we want to use a different perspective which entails a different solution technique. So remember, with column generation we have this concept of a path. So what if we define a unique cutting pattern in our role as a path? And to do so we can get all the items that were requested, and we can only identify the unique items in terms of length. And we still call this set I, but now it's only a subset of the original set. And with QI we define how many items of a certain length are needed. Let me be more clear. Let's assume this is the overall set of items we need to cut. But if you see, we have three distinct items. We have a first item with a length of 2, so the orange one, and we need 4 pieces. We have a second item of length 5, we need 4 pieces as well. And we have a third item of length 8, and we only need 2 pieces. So I, as a set, contains 2, 5, and 8. So in other words, the unique lengths among all the original items. And we have the 3 quantities needed. Q2 is 4, Q5 is 4, and Q8 is 2. And for example, we can define m initial paths in our problem, where for each path we cut a bin as many times as possible given the length of the current item, like this. Say we have an item of length 2, as we discussed. We have original paper roll with a length of 20. A pattern could be, I can actually cut 10 times this item here. If we consider our second item, so length 5, again 20 is a multiple of 5, so we can have a pattern with 4 replicas pretty much. But if we consider our item with a length of 8, we can cut 2 pieces, but then there will be waste. Actually, with this example it wouldn't really be a problem because we only need 2 pieces of this size, but maybe, and this is where the next slide comes into play, that waste could become something which is not wasted. So what if we start mixing items in the same pattern? So what if now a pattern is not only a replica of the same item, but what if we combine different items in the pattern? Of course, we still have a constraint, which is paths must be feasible. Like we saw before, we cannot add items to form a path that exceed the length of the path, which is the length of the bin or the paper roll we are considering. So, what's the path-based formulation of this problem? How does the path-based formulation of this problem look like? We have 2 sets. Set I, which again, remember, is a set of unique items, so the subset of items with unique distinct lengths. And we have P, which is the set of paths. We have some parameters. We have the length of an item. We have the quantity needed for that item. We have the length of a bin. And then we have it's actually a matrix. You can use other definitions. I'm using this matrix definition, MIP. And that's a matrix whose element IP defines the number of times item I is included in path P. And then we have a set of decision variables. So actually, let me provide you an example. In this case, if this was path P, and remember items are 2, 5, and 8, MIP in this case would have 1 for the first item, 2 for the second item, and 1 for the third item, because item 1, so length 2, appears once, item 2, which is length 5, appears twice, and item 3, which is length 8, appears once. Going back to the decision variables, XP is an integer, and it represents the number of times path P is chosen in our final solution. Here, this is our path-based formulation of the problem. We want to minimize the summation of our XPs. And remember, each XP defines how many paths we use, which means how many beans we use. So here we are minimizing the number of beans we use. And the only constraint we need to enforce is that basically overall, if we consider all the paths and all the items in each path, overall we are producing at least as many pieces of each item as needed. So this is a greater or equal type of constraint, which entails that we can produce, if we have a bound, let's say, of 4 for a certain item, we can produce 4. We can even produce 5. I mean, the fifth one will be not assigned, but we cannot produce 3 because we would be short on the demand side. So again, we want to minimize the number of beans, and we want to select the number of paths in a way that satisfies our demand requirements, pretty much. And again, this is a recap also from the previous video. Now we need to recall duality theory. So again, in a nutshell, if our primal problem, so this problem, is mostly horizontal, then the dual will become mostly vertical in terms of constraint matrix. A minimization problem becomes a maximization problem. The objective value coefficients of the primal, they become the constraints right-hand sides of the dual, and the objective value coefficients of the dual are actually the dual values of the primal. So, how many duals do we have in this problem? In the primal, we have I constraints, 1 per unique item, because we need to produce at least as many items of a certain length as the demand requires. Hence, for each of them, we'll have a dual, which we call lambda I. And we can actually write the dual as follows. So we want to maximize the summation of qi times lambda I, such that this set of constraints is satisfied. But do we actually need to solve this on our own? No, because when you're setting up and solving a primal, commercial solvers like Groby and Cplex automatically can output the dual values. So this is something which is solved behind the curtains. You don't have to model it yourself, but this is how it would like for this specific example. So, but what the dual values tell us in the end? Each of them basically gives you an indication of how profitable it is to add that associated item to a new path. So, but how can we use this notion to actually determine the best path? What we do is, again, remember, we need to set up a proper pricing problem. And in this case, we want to use the dual values as the coefficients of our new decision variables, yi, where each yi defines how many times a certain item should appear in the new path we are trying to compute. So let's take an example where we have 5 unique items of length 2, 3, 4, 5, and 6. And let's say this is the path we computed in the end. In this case, the variables would be as follows. y2 is 3 because item 2 or item of length 2 appears 3 times in our generated path. y3 is 1. y4 and 5 are 0 because there's not a single item of length 5 or 4 in our new path, and y6 is 1. So this is how we map the new decision variables into the actual path. The only constraint we need to add in our pricing problem is the path we want to generate is feasible. And this is actually how the pricing problem looks like. We want to maximize the contribution, the overall contribution, which is given as the linear combination of the dual of a specific decision variable times the associated decision variable, such that the only constraint is whichever path we are defining, we need to stick with the overall length of the bin. We cannot exceed the length of the bin. But the question is, shall we add any path that results from this problem, from this maximization problem? Actually, no, because again, if you recall the dual theory, we want to add a non-basic variable should become basic if and only if the reduced cost c minus z is actually strictly smaller than 0, where c is the original cost from the primal and z is the reduced cost we just computed above, pretty much. And if you remember how the primal, so the original problem, looks like here, In the objective, each variable defining how many times path P appears has a 1 as a coefficient. So our original C is 1. While from the pricing problem, we get that C. That C is the linear combination of the lambdas times our y's. Hence, we want to accept the new path if C minus Z, which is 1 minus that summation, is, again, sorry, strictly smaller than 0, which implies you are looking for a linear combination of the duals times y, which is strictly greater than 1. So this is how our column generation looks like. We initialize our RMP, again, restricted master problem, we compute the duals, we solve the pricing problem. Did we manage to find a path where the output of the maximization is strictly greater than 1? If yes, we had the path to the restricted master problem, we solve the problem again. As soon as we cannot find such a path any longer, we are done. And now let me show you a simple example. Let us assume we have a set of paper rolls of length 9. And let's forget about, it could be meters, but let's just forget about dimensions here. Let's say we have the following demand. We have, I should know, but I think it's 7 unique items of length 2, 3, 4, 5, 6, 7, and 8. And the quantities as follows. We have 4 for the length of 2, 2 for the length of 3, 6 and 6 for 4 and 5, and 2 for pieces of length 6, 7, and 8. So the question we are asking ourselves is, what is the minimum number of paper rolls we need to cut? And this is how we can set up the problem. In this case, it's Python via Gurobi. Let me activate the laser pointer. These are the original paths I'm using to feed the original RMP. So each row, let me describe to you what each path entails. So this number here is the number of times a piece of a certain length appears in my path, and these are the lengths. So again, 2, 3, 4, 5, 6, 7, 8. So a path 1, 0, 0, 0, 0, 0, did you say 6 times 0? Let's say 0, means a path with one item of length 2, so the first element here, and then all zeros otherwise. If you see here, what I'm doing is I'm not being very smart initially. I'm producing a lot of waste because this is my initial set of paths. I'm defining one path with only a cut of 2, and basically here I'm using meters, so let me use meters, and basically I'm wasting 7 meters. Here it's a cut of 3, this will be the second path, the second element corresponds to the second length, 3, and so on and so forth. Of course, there's a few cases where I can't do any better, so in the last path I have one piece of length 8, I couldn't add anything here anyhow, because the shortest other piece I could add would be 2 meters, but I would be exceeding the length of the bin, and again that would cause an infeasibility. So this is my initial condition in terms of paths. This is the length of my bin, the length of each item, and our demand. So this is how I set up my problem. I define a master problem, I define as many decision variables as the paths I have available. Here I'm defining an upper bound of 30, it could be better tightened, it's not really relevant here. And I'm defining my demand constraints. Again, it's a greater or equal type of constraint because for each unique item I need to produce at least as many items as required. If it's more and if it's optimal, okay, it means there will be some waste. Then my objective is very simple. I want to minimize overall the number of bins I'm using again, right? And it's very clear from here it's a minimization problem. So this is the restricted master problem, the initial one. Now this is where column generation comes into play. I'm setting an initial exit condition which is false and just a counter. And while the exit condition is false, and here I'm also setting an upper bound of the number of iterations, which is not met in this case. First, I need to relax my master problem. I didn't specify that here, but here I'm defining, as they should be in practice, my decision variables as integer. But in order to compute the duals, please remember they should be continuous. So this command right here, linear relaxation is equal master.relax, that takes any problem you have and relaxes every decision variable which is non-continuous. So this is actually what we want. It's quite a useful command in this context. Then we optimize this linear relaxation, and this is where we basically compute the duals. As I told you, you don't need to compute the duals by setting up the dual problem. Gurobi and Cplex, they have their own way of very easily, this is a one-liner, it's very easy to compute the duals, which I call in this case PI. I'm not using the same notation as the model, apologies for that. This is where I set up my pricing problem. I didn't tell you, it's basically a knapsack problem, that's why I call it knapsack, where I define my y variables. Here I think I'm being consistent, and basically the only constraint I need to impose is whichever path I define, it should be smaller or equal in terms of overall length to b, which is the length of each beam. And here I'm doing something a bit different for the objective. Remember, let me go back. Here I told you this is the problem we are solving. We are maximizing this, and then we are checking that 1 minus this is smaller than 0. So why don't we directly set up 1 minus that summation as our problem and we minimize it? What I'm saying is, instead of maximizing this, I'm already minimizing 1 minus that summation, which is equivalent, because 1 is a constant and maximizing minus something means minimizing that something, so that I can directly check if my final objective is negative, that's a path I want to add. And again, here I'm basically setting up my pricing problem. Here I'm solving it, sorry. And here I'm checking, is the solution negative? So again, given how I define my objective, I don't need to check if that objective is greater than 1. I can directly check, is it smaller than 0? If so, I'm basically defining a new path. I'm adding a new path as the list of paths I'm considering for the problem. And this is another nice command for column generation. I don't need to recompute the whole restricted master problem from scratch. I can simply add a column. Here I'm defining a column, which is a class in Gurobi and Python. It's like a new column element, and I just fill in that new element with the new entries I need. And basically I'm adding that to the master problem. It's exactly what we showed you graphically. With column generation, we are adding a column. Here I'm exactly doing that with Python. I'm generating an empty column, I'm adding terms when necessary, and I'm adding, of course, the associated new decision variable, which carries its own column. This is what I'm telling you here. And I'm also adding the number of paths here. This is just a counter, let's say. See here, if I find a negative value, I need to go on. Otherwise, that means my column generation stops, because there's not a new path which is deemed appropriate by the column generation algorithm to be added. So here I'm activating the exit condition. Here at the end, I'm rebuilding the master. Here I could have been smarter. You don't actually need to rebuild the master because you already have all the information you need, but I'm doing this just to play it safe. I'm adding all the paths. Now this is different than the initial one. Here we added some paths given our column generation iterations. I define my constraints. Again, I need to satisfy a certain demand per item type, and I want to minimize my the number of beans I use. And then in the end, I solve the problem. And here, what I'm doing here, apart from the comments, which I used to remember what I was doing, is basically to reconstruct how each role looks like. Because again, my solution is not directly usable in terms of how does a role look like. And let me show you actually what the iterations look like. So hopefully this is a bit more clear. These are the first 4 iterations of column generation. In the first iteration, I'm adding this path, which is 4, 0, 0, 0, oops, sorry, 0, 0. But again, this doesn't mean this is a path with a length of 4 and then nothing else. That's why I needed that last step before, that rolls 1 step with the reduced cost of -3. Then I have a second path, 1, 2, 0, 0, 0, third and fourth. How do they look like? This is actually path 1. 4 in the first, as the first element means I'm adding 4 times my first item, which has a length of 2. So that's why you see this path. This is the second path I'm adding. The third path, the third element is 2, 3, 4. So I'm adding 2 elements of length 4. This is the fourth. Then I have some more iterations, 5, 6, 7, 8, which entail this, 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 and this new path. And my last iteration was iteration 9 with this path. 3, 1, so 3 items of length 2 and 1 item of length 3. And as you see, usually it's like this. The reduced cost increases, so it gets worse given our goal as iterations proceed. And this was the last iteration I could, where column generation was activated. So now we had our initial set of paths, and we added 9 because we had 9 column generation iterations. But since we're adding paths that have the potential, according to dual theory, tells us to be useful, does this mean that they will all be used in the end? Of course, it's a rhetorical question. A bit counterintuitively, maybe the answer is no, because if we plot what the roles actually look like, this is the outcome. We have one role with 2 pieces of 2 and 1 of 5. We have 2 roles with 2 pieces of 7, of 2, and sorry, we have 2 roles where we have 1 piece of 2 and 1 item of 7. We have 2 roles with an item of 3 and an item of 6. We have 1, 2, 3, 4, 5, 6 equivalent roles with an item of length 4 and 1 item of length 5. And we have 2 roles with a single item with length 8. So overall we have only 5 unique paths, although we had an initial set which was 7, plus we added 9. So overall we created 16 paths, but in the end only 5 were used. And a final note on the quality of the solution. Now we are just disregarding any formulation, okay? So can we compute a lower bound regarding the number of beans or paper rolls we need? Actually, yes, because if we sum all the lengths of all the pieces we need to cut, and we divide it by the length of a single roll, and we use the ceiling operator, we get 13. So this is the length of all the pieces of length 2 we need. This is the length of all the pieces of length 3 we need, and all the way up until we hit the length 8. This numerator divided by 9, which is the length of a single bean, with the ceiling operator outputs 13. But if you check here, 13 is also the number of beans we ended up computing with column generation. So in this case, without even solving the bean packing formulation, we know our solution is optimal. But as I told you already, this is not the case in general. So here we got lucky, so to speak, or the problem was simple enough. But we cannot generalize this. Using column generation only in the root node doesn't entail our final solution will be optimal. And this is a take-home message I want you to take home.